will be a local speaker. Nicola is coming from Nordita, which is very close.
So it's that direction?
Yeah.
Ah, I thought it was there.
And so he will talk about, again, some statistical physics on the network systems.
Yes, thank you. Thank you very much for inviting me. I'm part of WINC, which is this newly created group at Nordita, and we do all sorts of things. Some people do quantum information, and other people do networks. And today we have 3 people from WINC, and also Henry is going to join us. And today I will talk a bit about my project, my PhD project that I've been doing with Valerio Lucarini. Usually most of the research is regarding response theory and climate, and then Grigorios Pavliotis at Imperial College that does interacting systems. And today I will talk a bit of how to merge these 2 things and why is this is helpful. So what are these interacting systems? We have seen a few today. And basically it's our hope as mathematicians or physicists or as modelers to have a kinetic perspective, a microscopic perspective on collective behaviors. And interacting systems are basically an ensemble of elementary components that are interacting with each other and possibly lead to complex and organized behaviors. The applications of these systems are all over the place in science, starting from synchronization, like we saw today, of nonlinear oscillators or phase oscillators we saw today, but they're used also for less physical systems, let's say. So they can be used for sociology, opinion dynamics, and basically they're all over the place. And we'll see some applications of this. The systems that we are considering, that I've been considering, are called weakly interacting diffusions. And again, we've seen a few today. Basically, you can think of it as, does the person? Yes. So their dynamics, there are an ensemble of agents. The dynamics of each agent is specified by 3 components, let's say. There is a local dynamics, and this local dynamics is given by a vector field F, which could be, in theory, whatever you want. So it could be simple potential landscape kind of thing dynamics, or it could be chaotic. And that's, for example, applications to chaotic nonlinear oscillators. And we also allow some sort of quantity disorder in the dynamics of these agents, meaning that each agent is, we assign to each agent a parameter or a set of parameter H, and the set of parameter is drawn from a distribution mean. So we are basically modeling the fact that these agents are non-identical. Also, each agent has some sort of noise, and this noise could possibly be state dependent, leading to some more complex behavior. But the interesting thing here is that these agents are coupled, and the coupling is proportional to the strength, theta, which is the strength of the coupling, is inversely proportional to the number of agents that we have in the system. And the functional form of the coupling is an interaction kernel K, which is pairwise interactions. And we take this so it's a big class of systems. We take this kernel interaction to be reciprocal, meaning antisymmetric, so it satisfies third Newton's law. And we have an underlying network topology. These systems are interesting because, as we saw before, in the thermodynamic limit, when we have a lot of these agents, they exhibit phase transitions. So we have this change of macroscopic collective behavior as some of these parameters of the systems are changed. And basically, it's an interplay between the parameters of the local dynamics, the interactions, and the noise. This project was to gain some analytical behavior in this kind of systems, and this is why we take, so far, we've taken the assumption of having a complete graph, which means that it's a complete mean field model, so there's actually no network topology underlying. or they could also be applied to whenever you assume some kind of mean field approximation to a network model. So basically, you replace the adjacency matrix with some kind of average behavior of the network. I don't know, mean connectivity, for example. And now what I've been doing, but I don't have many results yet, I've been looking at generalization of these results to systems that are described by an adjacency matrix that can be derived from a graphon structure. And a graphon can be thought of as a continuous limit, a thermodynamic limit of a network.
Are these interactions symmetric, or you?
The graphon structure, you mean?
Yeah.
So what we have is like complete graph, so, but they can be not symmetric as well.
Ah, okay.
It could be. Do you mean for the generalization to the graphon structure?
Yeah, I meant that it's a difference if you have symmetric interactions. So J with K is the same interaction strength.
So the kernel is antisymmetric, but this adjacency matrix could be, in theory, it doesn't need to be symmetric.
Okay, thanks.
But as I said, in this talk, it's going to be mean field models so far. So complete graph or very, very dense graph, which is a graphon structure. So mean field models are not exactly completely useless. They allow us to have some analytical insight, and two, they have been used in various contexts with some kind of success. And I just wanted to mention these two applications of neural networks, either artificial or real. And the first application is that mean field interacting agent models can be thought of as an optimization for a neural network. Basically, in machine learning, what you have is you want to estimate some kind of target function. You have this function f that you want to estimate, and you want to give what is called a neural network approximation of this function. So basically, you fix some kind of functions phi, and you have some parameters c and y, and basically you estimate your target function with this neural network approximation. And the goal is to find the parameters that basically give the best approximation of this target function. To do so, you introduce a loss function, and this loss function is just the mean square error, basically. And you give some kind of dynamics to this to optimize this loss function. And one of the most used ones is like stochastic gradient descent, where you optimize these parameters by going through stochastic dynamics in a complex landscape. And these dynamics can be seen as an interacting mean field particle system, where the parameters of the networks are the particles, and where the loss function is actually the interaction structure, the kernel structure among them. And this has led some kind of researching to find dynamical version of the universal approximation theorem, if you're familiar. But also, I wanted to mention that mean field models have been also used with some kind of success to describe a macroscopic behavior of some kind of processes in the brain. And I've just put a few models here, and we've seen some today in the first two talks. So why are we interested in these mean field models? Basically is because we can find in a thermodynamic limit what is called a hydrodynamic or a mesoscopic description, so a simplified description of the system. And basically, if you think of the n-particle system as being microscopic, you can think that you have very little hope to actually study each trajectory of these of the ensemble of agents. But maybe you hope that you can find a closed description for mesoscopic observables. So basically, you take some observables of the mean field observables of the system, and you hope that you can write a closed equation for them. And the paradigmatic observable of a system is usually what's called the empirical measure. So rather than looking at the individual trajectories, you look at proportion of particles that are in a specific phase space region. And actually, this hope is true for these mean field models because of this propagation of chaos, molecular chaos, which is, we should say, effects that have been also described in the first talk today. And basically, this is a property of these systems in which you have asymptotic statistical independence. So as you reach, as more and more connected agents there are in the system, the more statistically independent they are, which is kind of a counterintuitive mathematical property of these systems. But this is not just a mathematical property. I was attending a talk, and the speaker gave a nice example regarding brain dynamics, neural dynamics, and this example is taken by Ecker et al. In Science 2010. And basically, they showed that if you look at some activity of local groups of neurons in V1, and you look at the correlations of these neurons, of this ensemble of neurons, you might think that being very close to each other and having very common strong inputs, these neurons might exhibit some strong correlation properties, but actually, as you can see here, these correlations, which are called RSC, are very close to zero, meaning that the more neurons you have, the more statistically independence you have. In mathematical terms, and this is there are different ways to see how this happens, but the easiest way for me is to say that if you have the complete microscopic system, which is described by an n-particle distribution, then propagation of chaos happens, and it means that this n-particle distribution in the thermodynamic limit factorizes in identical single particle distribution rho, and mu I noticed just the distribution of the quench disorder, and that's identical. But the important thing here is this distribution, single particle distribution rho, that satisfies a McKean-Vlasov equation. And today in the first talk, the McKean-Vlasov equation was called the continuity equation, but actually this property is not just for the Kuramoto model, it applies to general models, to general mean field models. And this McKean-Vlasov equation has a Fokker-Planck structure. So you can see here the local dynamics of each agent and the noise, but it is nonlinear and non-local, meaning, and you can see it from here in the interaction part of this equation, we have a convolution term, you can see it here, between the interaction kernel and the probability distribution itself. So the drift term of this equation depends on the probability distribution. That's why it's nonlinear. And also I want to say that the quench disorder has a simple effect in this equation, which is just integrating overall values of this disorder, overall the ensemble of agents. And being nonlinear and non-local, this equation doesn't satisfy the usual Fokker-Planck equation result. So basically, for some specific values of these of the parameters of the system, you might have coexistence of invariant solutions. And actually these, as you change the parameters, these invariant solutions might lose their stability, exchange the stability, disappears. And this is what we call in this framework phase transition, which are usually called phase transition. And again, we saw some phase diagrams today. They could be, they are related to this. So how, the question was, how do we detect phase transitions in general systems? Basically, the first thing you need to do is you identify an order parameter. And an order parameter is basically just a collective variable that you use for complexity reduction. Basically, an order parameter is an encoder that takes the full state of the system and projects it down to some kind of reduced and hopefully optimal description of the system. So basically, you hope that your system can be described in terms of few variables or few order parameters. And if you want to verify that this is a good order parameter, then you change the parameters of the system. And in the thermodynamic limit, you hope that this order parameter has some kind of abrupt, sudden change. And in equilibrium physics, you might use symmetries of the problem. But in general, if you have high-dimensional non-equilibrium systems, you don't have these symmetries. But also in systems that don't really have a physics-informed dynamics, how do you come up with order parameters? And this is kind of problems. For example, for neuronal dynamics, there are all sorts of different models, and it's not easy to identify one-to-one what a good order parameter is. And we were inspired by this question to approach this question by using response theory. Because of this, changing some kind of parameters of the system and looking at how observables react. And in particular, we wanted to apply response theories to interacting systems. If you don't know what response theory is,
Can I
yes.
ask you a quick question? So this order parameter in context of networks and some dynamical model and networks should be dependent on the model. That's what you say.
That's true. That's true. For example, for the Kuramoto model, there is this classical order parameter Z that was introduced firstly by Kuramoto, and you can show that this one has nice properties, but it was made up by Kuramoto. Then you can have some physical insight on this, but in general, you don't have these kind of order parameters, and it's model dependent. So response theory, if you're not familiar, it's been mentioned today a few times, but basically it was developed initially for statistical systems that were near equilibrium. But actually, and this was 60 years ago, 50 years ago, it was expanded to include way more general systems, including non-equilibrium, highly dissipative systems that show chaotic behaviors. And now it's like a pillar of stochastic processes as well. And basically the goal of response theory is to predict how the statistical properties change of a specific system as you apply some input to it. And basically, in other terms, response theory tries to find relationships between what is called forced variability, so the variability when you force the system, when the system is forced, and the unforced one, so when the system is unperturbed. In mathematical terms, this is if you have your system here described by a generic stochastic differential equation, you might think of perturbing the system, the local dynamics of this system by, for example, applying a small in amplitude perturbation, but this perturbation could be very generic. It could be state dependent, it could be time dependent. And in less mathematical terms, if you think of having like a network of neurons, this network of neurons has its own dynamics, and then you might think that in one node of this network, you apply some kind of perturbation, or actually this perturbation could be the output of another part of the network, the neural network. And then you might ask yourself, okay, I've been applied the input on node 1, how does this affect node 6, for example? This is a classic question of response theory. And mathematically, this means that you want to look at the focal Planck associated to this perturbed system, and you can decompose it in an unperturbed one and a perturbation to this. And the idea of response theory is that you take an observable phi, and you ask yourself, how does the expectation value on this perturbed system changes with respect to the unperturbed one? And in linear approximation, you write this. So it's the unperturbed one plus some kind of correction. And this correction can be explicitly evaluated through a convolution between what is called a Green's function and the time-dependent modulation of the input that you applied, that it's been applied to the system. And the Green function has this explicit formula. You have a Heaviside function that enforces causality on the system. And I don't want to get into the details of this, but the green functions basically depends only on the properties of the unperturbed system. And this is why the linear response is useful, because from the unperturbed system, you can find properties of the perturbed one. And of course, it depends on the details of the state-dependent perturbation that you've applied. And in stochastic systems, you can show that a fluctuation dissipation theorem holds. Basically, you can write the green functions as a correlation function, as we saw before, in the unperturbed system. But these correlations are non-trivial. For equilibrium systems, these correlations are known. Rather, for non-equilibrium systems, the functions happening in the observables in the correlation functions are not known. So one can apply this whole machinery, and as I said, the Green's function is exactly the mathematical quantity that tells you how an input on node 1 affects the statistical properties of node 6. But rather than looking in time, one usually introduces a susceptibility, which basically is just looking at the response of the system in frequency space. And it's very easy to see by taking the Fourier transform of the previous equation that the response of any observables at frequency omega is basically the time modulation at frequency omega modified by the susceptibility of the system. And this susceptibility chi has a very physical interpretation. Its amplitude, it's a complex quantity, and its amplitude is an amplification factor of the input. And the argument of this complex quantity basically tells you the phase factor of the output signal. And it's a classic result in ergodic theory that now has become way more useful in applied mathematics community through the, if you're familiar with it, the Koopman operator and Koopmanism approach. Basically, you can just by looking at this formula, you can see that the Green's function depends on this operator here, where L naught basically is just the adjoint of the Fokker-Planck operator. And it's been realized that the properties of the Green function can be decomposed in terms of spectral properties of this transfer operator. And in general, this transfer operator, this Koopman operator, has a point part, a point spectrum, and a continuous spectrum. And the continuous spectrum usually in application is neglected, while the point spectrum has a direct one-to-one physical correspondence with physical properties that you observe. For example, you can see here you have a sketch of a typical spectrum of these transfer operators. The point spectrum that you see here, or you see here in the red dots, they correspond to peaks, to resonances of the susceptibility. And the closer these eigenvalues are to the marginal stability line, which would be the imaginary line here, the narrower and the more divergent these peaks are. And the position, of course, of these peaks is given by the frequency of these eigenvalues. So basically, in the talk before, these were related to the matrix, the random matrices. In nonlinear systems, you kind of need to go to a level above, and you need to take into account the nonlinear dynamics that is happening and taking transfer operators. But basically, there is this one-to-one correspondence of eigenvalues and resonances of the susceptibility. And a resonance of the susceptibility is just an enhanced response to perturbation. And when these eigenvalues get closer to the imaginary axis, what you obtain is that these resonances, they become more and more diverging, And basically you have exactly on this line, you have a divergence of response theory, meaning that a small input in your network will create, will basically, it means that the negative feedbacks of your network become less and less effective. And so this small input will create a very huge effect on the network, which was the criticality phenomenon that we discussed in the first talk. And so we have this critical slowing down of observables where a small perturbation doesn't get reabsorbed quickly in your system. So how does this look like in interacting system models as we've seen before? We know that we have this mesoscopic description given by the McKim-Vlasov equation, and the McKim-Vlasov equation is infinite dimensional because the drift term depends on the whole probability distribution. And before we saw examples on the Kuramoto model where it's kind of a very particular example of this because you have the Ont-Antonsen ansatz that basically allows you to reduce the dimensionality of the problem to very few equations. But this is not the case for all these systems or all these models. But we realize that if you ask a very simple property regarding this kernel, and you ask that this kernel is separable, so meaning that rather than being a function of x and y, it can be written as sums of functions that depend only on y and functions that depend only on x. And this is, for example, a case for linear forces. So forces that depend linearly in your variables. And you can think of this as we were seeing before, like the synaptic structure was linear in the output of the other neurons. Then we can show that you have this encoding given by exactly these functions A. So basically, you can write the McKim-Vlasov equation in a form where the interaction part does not depend on the full probability distribution, but just on a few and finite numbers of observables A's. And these observables are exactly the ones happening in this decomposition here. For linear forces, this looks like this, and basically the observable A that you should look at is, yes.
So just about this description you're explaining right now, a small curiosity. At the beginning, when you wrote the stochastic differential equation, you had multiplicative noise. You had the sigma of x, but here there is sigma squared divided by 2. So where did the multiplicative noise go?
Good point. But it's not a problem. Here you have this delta with a tilde. That is just a generalized diffusion term. The thing is, the noise itself didn't depend on its local. So it's the same for each of the agents. So it doesn't make all the agents interact. So you don't have any interactions through the noise.
So that is like the second derivative multiplied itself by
exactly. So exactly. So here you have the second derivative and then the diffusion matrix.
Okay, thank you.
But the difficulty of this McKim-Vlasov equation is that you have the interaction term. And if you take a separable kern, then you can show that this interaction depends only on a few observables, macroscopic observables of the system. And for example, for linear forces, this is just the first moment. So it's the empirical average. And so far, this is just a mathematical property. But actually, we can show that these observables are good encoders, meaning that they carry a lot of important properties of the system. They, in fact, carry correlation and memory features of the system, but also they determine the resilience of the system to perturbations, meaning, and more importantly, they fully characterize the development of these critical phenomena or these phase transitions. So basically, they are good order parameters of the system. And we investigated this, as I said before, through response theory. Yes.
Could you go back to it? Could you give me an intuition why these good order parameters would be exactly those that factorize your kernel? What is the intuition behind these being good order parameters from?
So the mathematical step of going from this equation to this equation is just, and it's a convolution product. So you can see that the only thing that survives in the convolution product is this one, are these functions. But why these functions are good observables, this we can only understand through a linear response perspective, which is going to happen.
Okay.
Yeah.
Thanks.
We don't know that yet. No, it's the next slide. So basically, I won't redo the whole machinery response theory for this system, but the idea is that you have your system of agents, you apply perturbation, and this is the perturbation, and you observe the response of some variable. And of course, here the natural variable that you want to observe are these collective variables that we defined before. And why is that? Because if you look at the response at time t, the response of this system is a bit more complicated than an usual one that we saw before, because it can be written in two terms, where one term is similar to what we saw before for finite dimensional system, where you have a convolution between a Green's function g and the time-dependent external perturbation. And we can show that this Green's function can be thought of as the response of a single mean field agent in the networks, in the ensemble of agents. And of course, this depends on the perturbation, on how the perturbation looks like, and we can attribute this to exogenous. So exogenous processes, so something that depends on the properties of what the input that we're applying. But then there's a second part, and the second part is due to the coupling, because you can see it here, that is proportional to theta, and it depends on all the other reaction coordinates, the collective variables that we defined before A, that are happening in the system. And this is mediated, this response that you see here is mediated through a different Green's function that we called endogenous, because it's just related to properties intrinsic to the system. And as you can see here, this term here, this response term here, can be attributed to memory effects that are happening in the system. And these memory effects, why are there? Because you have the value of the collective variable at time t. It depends on all the previous values of the other collective variables at previous times. And this is something that physically, this means that basically the response that you have in the system gets bounced around between the different agents and leads to this memory effect. It's easier to understand this if you, it's easier to disentangle these two terms if you look in frequency space. And so, as before, you take a Fourier transform of that, and you can say that the response of the collective variable at frequency omega is just the input at frequency omega modulated by susceptibility. And this susceptibility function is not simply that you see here, this tilde chi, is not simply the susceptibility of a single agent, but it's modified by a matrix P, the inverse of P, that depends only on the endogenous Green's function of the system and describes the feedback that are happening in the system. And it's easier to see in a picture rather than in maths, but basically the situation that is happening here is that you apply the system, an input to the system, and this input is modulated by the single susceptibility of each agent, but it's not simply that. There is also feedback given by these endogenous Green functions, and this feedback, the whole thing, it represents the actual susceptibility of the system. And that's how you evaluate the output. As we saw before, we can distinguish two different regimes of response of the system. You can have a smooth regime where this susceptibility function is a well-behaved function with some resonances describing the enhanced response of the system to certain perturbations, but there are also critical regimes. And these are the ones that we're interested in. And the critical regime was, as we saw before, was characterized by singularities of these susceptibility function that were developing by the fact that these eigenvalues were crossing the imaginary axis. If we apply the same framework here, we can see that a singular value of this susceptibility can come from two different effects. Either the single agent susceptibility, and this means that if you apply a perturbation, each agent, basically you're destroying each agent of the ensembles. But if the singular behavior comes from this function here, it means that you apply a perturbation, the single agents are well behaved, the single neurons, if you want, are well behaved, but the response of the whole ensemble is critical. And this is what we identify as a phase transition. So phase transitions are characterized by the criticality arising from this part of the susceptibility rather than this one. But anyways, we claim that a signature of criticality in these systems can be identified as, as a general case, as a simple pole of the susceptibility. So the susceptibility at criticality can be written this way. And we identify two typical scenarios. One is when this pole is 0, and where you have a static phase transition. So basically, the system doesn't exhibit any oscillations. And the other typical scenario is when these poles are symmetric, and you have a pair of these, meaning that you have some oscillations happening in the system. And this was a very mathematical theory of general classes of ensembles, and I want to show you some examples. We saw before the Kuramoto model, and so I won't spend much time here, but basically you have agents, and each agent has a intrinsic frequency, and then these agents are coupled together, and there's also noise. This Kuramoto model shows separable interactions because the interaction kernel is just a sign, and it's been shown before that we have an incoherent state where all the oscillators oscillate at their own independent frequency, but they don't synchronize together. And we were interested in understanding how if this signature of criticality was shown by these systems when the incoherent state was losing stability, when you have a phase transition towards synchronization. And this is exactly what we observe in simulations. Here you can see, in this panel here, you can see the Green's function of the system. In black line, you see that the Green function, the black line refers to non-critical settings. So you apply perturbation and then the perturbation gets reabsorbed by the ensemble very quickly. But then at critical settings, the perturbation decays on longer and longer timescales. And actually these timescales depend on the number of particles n that you have. And of course, this is the smaller number of particles, this is bigger number of particles. And these, you can also evaluate the susceptibility of the system. And as you can see, we have a diverging behavior of these susceptibility in omega equals to 0, meaning that this phase transition can be identified by a static phase transition. And the only thing that I wanted to say here is that before we claim that criticality can be written as a simple pole of the susceptibility. In fact, this shows that in finite systems, what we observe, of course, is not a diverging behavior, but what we have is a moldifying singularity. So a singularity becomes a resonance because the finiteness of the system basically shifts down the pole, and what should be a singularity in the thermodynamic limit is just a resonance in a finite system. But still, this let's call it signature of criticality holds. And of course, we looked at different kinds of phase transition of the Kuramoto model. For example, in this case, you have dynamic phase transitions where the susceptibility diverges, is diverging, or at least gets a resonance at a non-zero frequency. And I just want to say that this signature of criticality hides the features of the phase transition also in what is called the residue. And the residue one can link to how this response of the ensembles are in or out of phase with respect to the applied input. And then I have some other models that we looked at. This model is a double well potential. So it's an agent that hops in between the two wells, but it also has some linear interaction among them. And we can show that it has a continuous phase transition as you increase the noise. And at the phase transition, you observe a similar signature of criticality of the system. And also I have another example here where we have nonlinear oscillators. So in this case, we actually have actual oscillators where you have an amplitude and a radius. And again, these are coupled linearly through their interactions. And as you can see here, there is a phase transition with a dynamical signature to it. And this is all I wanted to show. Just going to the conclusions, we've looked at mean field interacting agents of this type, where we have a mean field interaction. By looking at the interaction structure among the agents, we have identified some collective variables, and we've shown that these collective variables describe completely the response properties of the system through this formula here. And actually, we have characterized phase transition or critical phenomena of these systems as situations where you have a pole of the susceptibility that arises just from this part of the susceptibility. And so we claim that in finite system, critical situations can be written in this form, where the singularity in the susceptibility is modified by a finite size effect. Next step that I would like to do, and this will be interesting, is to extend this framework, which is mathematically rigorous, to situations where you have a network topology with a graphon structure. In this way, we could actually have a space, a topological space, a topology, sorry, and we could look at how a perturbation in some part of the network will affect the statistical properties of other parts of the networks. And that's all. Thank you.
One question: the results you show now for all these different models, there is these beautiful graphs. Are they for the simulation of the microscopic model to check the predictions, or are these just obtained somehow numerically solving the equations you get at the macroscopic level?
No, this is our simulations of the microscopic of the finite particle system.
Okay.
For different values of the number of particles.
Simulating the system. So then the omega star, I think this will be like the point in which you get like the phase transition when you make n equal to infinity. You can estimate this analytically from.
Yes. So basically, what you can do, I didn't show now, is that you can evaluate. Let me see. You can evaluate this matrix P. And by looking at points where this matrix P is not invertible, then you can find the omega where the phase transition happens. And of course, like for example, for the Kuramoto model, there are different ways to do this, and of course they need to agree with this.
But I guess it's not easy to do this process of checking where this matrix is non-invertible analytically, no?
Yes, of course, but it's the same complexity, I would say, of checking when you have when you want to study phase transition for the Kuramoto model. Then you have to find a spectral problem for a linear integral differential operator.
Yeah,
right?
it's the same. Like if you, instead of applying odd Antonsen, you get all the equations for that, and you want to have these metrics for the stationary
Exactly.
state, so on, so on. So it's more or less a similar problem.
Yes,
in the practical
but
terms.
it works. The odd Antonsen answers is very specific to certain types of models.
Yeah, yeah.
For other types of models, this has not been established. So you kind of need to find other ways to get there.
This frequency that you get because you have the finite size of pegs. I'm a bit puzzled by the fact that it depends on the system size. Can you give me an intuition? For example, in the Kuramoto model, what is this frequency? Is this the frequency
So
of revolution of the phase, or is it something more?
So if you, this part here,
Yeah.
so the frequency is still the omega star, what you obtain. For example, let me take this one. So for example, this is the Kuramoto model where you have a bimodal distribution of frequencies. So basically, either you have plus one frequency or minus one frequency, and these are the agents. And you can show that in this case, the Kuramoto model has a non-synchronized state, and then the non-synchronized state becomes, through a Hopf bifurcation, basically, something else. And the Hopf bifurcation in this framework is identified as a phase transition at a non-vanishing frequency, omega star. This omega star you can actually evaluate for the Kuramoto model. The thing is, what you observe in finite systems is that this you would have the singular behavior at omega star, but this singular behavior becomes a resonance, meaning that in theory you would have, as you were showing before, like an eigenvalue that gets on the line, on the linear instability line, right? Having a finite size effect means that that eigenvalue is slightly shifted towards, depending on the case, but towards a stable region. So basically this could be also interpreted as you have a you have a width of this resonance. This resonance is not a delta, but it's modified.
Okay, yeah. Now I see. Yeah.
So the peak is the peak of this resonance is slightly shifted, but really slightly shifted. The more important thing is that you have it's not a delta, but it's some kind of.
Yeah, you don't have a divergence, but
you have a
okay.
resonance.
I see. Thank you.
I have a last question. So I was wondering this condition on which you can apply. How could you extend it, or why it doesn't work?
So the condition, do you mean the separable condition?
Yeah, exactly.
So actually in most models, especially in synchronization of phase oscillator or oscillators, people either use sinusoidal couplings, which at any order are separable, or they use polynomial interactions, and linear to be the standard one for, like, as we saw before, for the synaptic interactions. So basically, most cases are separable, but there are situations, for example, in active systems, in flocking systems, where basically you use an interaction which is an exponential that is not separable. But there is a huge literature in which you can approximate a kernel as a sum of separable kernels. So in theory, this theory works exactly for separable kernels, but can be applied in a phenomenological way to those situations as well.
let's thanks Nicola again.